Okay, so we now would like to basically look at this equivalence between our previous cosine-sine form of the transverse magnetization dynamics and basically the equivalent form in terms of this complex exponentials. And of course the basic trick in this whole thing is again the complex exponential, so that e to the power of ix equals cosine of x plus I sine x, as we looked at previously in the Fourier business. So of course we are building on our knowledge of complex numbers, complex exponentials, and so on. So this is fairly straightforward to show. So let's start again with our form for mx and my, and again I suppress the dependence on r, because this again holds for all of them. So that's our x minus t, t2, and the same for my. And then we have our mx cos omega t plus my sine omega t. So that's again the solution we worked out last time, or we checked last time, I should say. And we have our cos omega t minus mx sine omega t, and our omega t is still defined as our omega 0 t plus our integral from, that's a gamma, not a y, that will be, and I suppress the dependence on space, so it's only a function of time. So that's where we start. We know that, yeah, so that's a given. And we now have this new definition of our complex signal over time, where I again suppress the dependency on space, which is given as mx t plus I my t. Yeah. So this is now, we can see that as a definition, so that our complex signal is defined as the first, or the x component of our transverse magnetization plus the what's it called, the complex unit multiple of the y component of the transverse magnetization. And if we now substitute these forms here, so these forms for mx and my, we are led to these complex exponential forms, and that we wrote down here. We're basically led here. And to show you that is then the aim. So if we now substitute for mxt this and for my this, then you see that both of them are multiplied by exponential minus t divided by t2. So we can from the start basically take this out of the two sum terms and multiply the entire sum by this. So then we're doing this in one step, so that we don't have to write up too much. But then we just substitute our mx. So that's omega t t plus my sine omega t, and add to that the I multiplied my. So let's do that here, plus I my cos omega t minus m close this bracket. And then we can basically, of course, resolve the brackets inside this somewhat longish expression. And so we multiply this I into here, and then we, or do we already? Oh, well, let's just do it. We want to somehow get to a complex exponential form with cos plus I sine equals e to the power of I x, and this is what we trying to do here. So we can take our here this I times mx sine. So we have minus I mx sine omega t, and then we have how do I do that there? Oh, that's fine. And here, okay, I'm going to make another trick. So we have this term, that's fine, and we have I m y cos omega t plus m y sine omega t. So basically,
there's also a plus between them, right? Mx.
This, yeah. So basically, I just this thing is this, and I m y cos is this, and my is this. So it's just the same terms. I mean, you can look at the details in 4126. Then you see it maybe a little bit, not maybe, you see it written up a little bit more cleaner, or a little bit cleaner. Then we can take the mx, so we have mx here and we have mx here, so we can take our mx out of this and have cos omega t minus I sine omega t, which is good. And here we can actually take the mi out, so this and this, and the I, so we do I y cos omega t, and then use also a minus I sine omega t inside this bracket. So if you resolve this bracket, you have I my times minus I sine. So I times I is minus 1. And this gets multiplied by a minus 1, so you have again plus my. Yeah, so that's the trick here, basically using to get also here a cos omega t and a minus I sine omega t, to have basically take the I out of the brackets and put another I in. Because then we have both a cos omega t minus I sine here and a cos omega t minus I sine here. So we can also take this out of the sum, or essentially write things as follows: minus t half. So we can write, there's again a plus, mx plus I my, and then only one term, cos omega t minus I sine omega t. So basically just, so if you again resolve the brackets, you get mx times this, So you get this first term here, and here you get then plus IMY times cos omega t I minus so you get this term back. So it's simplified. Then of course we can change the order of things if we want. So we can put this up front. We have our exponential then second, and then of course our cos omega t minus I sine omega t is what? No, so we have what we have here is now something that looks like this if you write it even simpler. So what is this? Yeah, and so exponential is correct, minus is also correct, x is also correct in this case. And so in this case we have omega t, but one thing is missing. The I, exactly. So this is just so if we do that here, so that's x minus ix. Yeah. Remember that we went over the series definitions of sine, cosine, and exponential at one point and showed that this actually holds. I think we showed it for the plus, but then we said it's fairly easy to also have that for the minus if you multiply by -1. So we have now basically gotten rid of our cos and sine and reformulated in terms of the complex exponential. But again, this is just because the exponential with the complex number is equal to the cosine plus the I times the sine. Then we already specified that mx plus I my equals mc. This is one of the definitions that we used here. So that's this thing. So this is essentially a definition. So mc, if you look at the real part of mc, that's mx, and the imaginary part is my. And we are now in this form, t2 x minus I omega t. And then finally we have to substitute again our form omega t. And yeah, let's just do that. So we have mc x minus t t2. And then our omega t was always the abbreviation for omega 0 t. So this constant frequency contribution due to the static magnetic field plus our integral of the time varying magnetic field due to the activity of the gradient coils. In the script, I think I have to throw out some r's. There are some r's too many because currently I'm suppressing them. So that's followed by substituting our initial definition, and then of course we can also resolve the bracket in there. So we have x minus I omega 0 t minus I gamma t 0 delta b tau d tau. And then we can use, what we can always use is that x a plus b is x a x b. And then we get mc x minus t t2 x minus I omega 0 t x minus gamma t 0 delta B tau d tau. And that's then exactly, where are we? This expression here. So this and again, it's just the reformulation of our solution that we worked out previously in complex exponential terms. So nothing happens really. It just looks different and maybe more complex, and it's more tailored to electrical engineering work that deals with complex numbers. And as we will see then in a not too far future, to Fourier business. Let's have a brief look at the implementation once MATLAB starts up. So these plots that I showed you previously, they result from this code. So again, I'm doing, let's see this roughly. I'm defining some time vector. So time is specified. I define some time constant, and then I'm basically in this lines just evaluating the transverse magnetization, again for our delta BRT or BT being 0. So here I have a 2D vector that I'm filling with this exponential times the cosine and the initial condition. So that's here. And of course I can also do the same thing with just a single number, but the single number is a complex number, so it has a real and imaginary part. And so this is what we just basically figured out. So I'm defining a complex number that has the mx and the my as real and imaginary part, so that's our MC. We have the exponential, and we have the complex exponential term, the other one with the integral of delta b, that's the 0, so the exponential evaluates 1, so it doesn't show up here. And here we have the complex unit. And now if you visualize that, you can either visualize the two numbers of the vector and plot them in 2D, or you can plot in 2D the real part of the complex number and the imaginary part of the complex number. And as we've seen previously, this is exactly the same thing. Yeah? So it's just a different way to write this mathematically, and it's the same thing. Yeah? Good. Questions right now? Good. No questions right now. So, of course, I wouldn't have done that if we wouldn't need it, and we will need it to get started on the Fourier imaging business. But before we do that, we now look at the signal equation again with our new complex exponential form and simplify that to a certain degree. So again, our the MR signal equation, like we discussed early on. is describes the signal that is acquired by the receiver coil. It's a signal over time, so it's a time-dependent signal, and that's weird. Did I write this morning as well? So it must of course be T gets allocated ST and not S gets allocated ST. Didn't make any sense. There are typos. Is anyone? Anyway, I remember that hopefully. So that's our space integral over the sample of our mx rt function, which is integrated over space. Yeah, so that's our spatial integral. And now we've found an equivalent expression for this, which we called MC RT. And we found that for a single location in space, this is why we suppressed the R for some time, but we can now, of course, put the R back in. And yeah, basically write out this integral. So what we get for our signal, so this the complex signal that the receive coil registers at each moment in time, according to our model, is now given as follows. We have our MC, which is our initial condition, and that is space dependent. We have our exponential decay with our space dependent T2 time constant. Remember, different parts of the brain have different T2 constants. We have our exponential contribution that is due to our gamma times B0. And we have our complex exponential contribution that is due to the space and time varying magnetic fields induced by the gradient coils. So I'm just plugging in the complex exponential form that we developed just 5 minutes ago into the MR signal equation right now, as you see. Yeah, so that's the signal that is registered by the receive coil at each moment in time, let's say after excitation. So you send an excitation pulse and you measure, and for each moment in time you get two numbers, the real part of the signal and the complex part of the signal, and the signal, the idea is that it's given by this. So this is again just this thing plugged into the signal equation. So it's this blue thing. Yeah. So that's essentially. So the idea is. So you can view this as a model. So the idea is that you sit there at the scanner, and the scanner records a signal at time t, and your idea what the signal represents is this. Yeah. Now it is a little bit, it's longish a little bit, and one can simplify it a bit. And before we then can really get to the 2D Fourier business, we need to, or it's helpful to simplify this a little bit. And the simplifications are as follows. Firstly, we assume that the T2 time constant is fairly long. So what does this mean, this exponential decay? This exponential decay means that the signal that we acquire decays. Yeah, so that's essentially what this contribution here does. So as time progresses, the signal gets lower and lower and lower. Now we can, of course, imagine that we acquire the signal. So this is just the signal, and we acquire the signal fairly early on before it has decayed a lot, so that the T2, so that our signal acquisition is happening fairly early on. Another way to imagine that is that we deal with T2 constants which are fairly long with respect to our data acquisition. So we have long T2 constants, then also the signal decay is negligible. The final way to think about this, if we get to it, this term, is that we actually can undo the signal decay due to using echoes. So in any case, these are three motivations why we can, for the moment, definitely set this to 1, so assume that there is no signal decay. So the real trick later on for why there is no signal decay is that we do some echo imaging, where we refocus, or not we, but the MR scanner refocus the signal and the decay doesn't contribute, or we are actually interested in the decay. For the moment, we just say there is no signal decay. So we assume that the signal stays strong because, for example, the T2 time constants all over the sample are fairly long. So that's good. Or that makes things simpler. So we assume no signal decay. Another thing that we assume is demodulation. Which means the following. Essentially, it means that the signal gets multiplied by a complex exponential of this form. What does that mean and what it's about? The thing is, this Lambda frequency is fairly high. I don't know, it's I think for protons I have in mind it's like 44 megahertz or something. It is not, it is the same, so it is the same throughout the sample, so there is no spatial information in it because it's just due to the nucleus. So another way that we are imaging, so another way to look at this is that there is no spatial variable in here. It's just, the signal is just oscillating everywhere due to the nucleus and the static magnetic field at a given high frequency. The thing is, we know what this frequency is because we know which nucleus we are imaging, and we know how strong our magnetic field is. The spatial information, the spatial contributions and differences in space are here. So this is just an overall spinning contribution that we might as well take out of the signal because we know what it is. Yeah? So we know, so if you think again in terms of sine and cosine, this term alone just describes a spinning movement that is not decaying, it's just doing this. And in addition, there are a variation in terms of phases or the frequency of spinning due to this term. But this thing is the same all over the sample. Yeah. So, and we know what it is because we know what the gyromagnetic constant of our nucleus is, and we know our B0 field. So we know that there is this contribution in the signal, and it's everywhere and it's all the time. So we might as well take it out. And this is done by essentially multiplying the signal electrically with this constant frequency term, and then also by this taking this out, so that the only thing that we see in terms of movement is, or in terms of spinning business, is this thing. Yeah, that's called demodulation. So the thing is, I mean, it's fairly simple actually. So there is in our signal, there are things that tell us about space, spatial information, that have spatial information, and in addition to that, there is a constant signal like that. And so that's our constant signal that we get from our B0 and our gyromagnetic ratio. And in addition, there are things that are of interest, so that that have maybe some spatial information. And the idea is that we just filter out, or essentially you can also view it as a filter, we just filter out this constant contribution and look only at the rest. Can also, another way to view this is that you have, if you want an EEG analogy, you have line noise. You have 60 Hz line noise in there. And this is described by this term. So you filter out, so you do a notch filter at 60 Hz or 50 Hz and get rid of it. Yeah? It doesn't have any information. Questions about this? That's called demodulation. Actually, you can read more about the technical details, how this is achieved in things like the Hake book and so on, also in the Nishimura. But the bottom line is that we get rid of this and we get rid of this. And a final thing that we get rid of is the Z domain. So remember that our R is x, y, z, so that this integral here is essentially dx, dy, dz. And what we assume now is that we do the whole thing in the presence of a z gradient. So of a z gradient that does not change with time. So we have here our z and we have a gradient. And by choosing our excitation frequency, so another way to look at this is that this omega 0 is again space dependent, but we only do it to excite and select a given slice of our sample. So we basically then look at the signal that is already average over Z. Okay, that I see that you might find this confusing, but it's actually fairly simple. So think again of the brain. There's the brain and the scanner. This is the brain and the scanner. The nuclei, I'm trying to also for our viewers at home. This is the brain and the scanner. According to B0 and our gamma, the nuclei precess with a given omega 0. Now, if we turn on Z gradient, the nuclei at different locations in the Z, so let's say that this is Z, precess at slightly different frequencies, which we can use at excitation. Yeah, so we excite at the resonance frequency. So by tuning our resonance frequency, we might select, because by choosing our omega 0 appropriately, we choose this location in space, and then we know that where we roughly are in space in terms of the Z direction. And then for the remaining spatial extension so because there's a finite width of what we have excited, we assume that the signal that we acquire is the average over the Z direction. Yeah, so we basically perform this integration over Z and leave present in the signal only the integration over X and Y. Yeah, so we don't know. So you have to ask if this is unclear, because I don't think I have the words to explain it in another way right now. So you can also view it as follows. So here, these are obviously three integrals, so x, y, z, dx, dy, dz, and we perform this integration with regards to z, and then we are left with an integral with respect to x and y. Or we say, okay, I'm running out of words to say that differently. So these simplifications So basically this, which leads to our x and y, and here to dx, dy, then lead to the following form of the MR signal equation. So again, now we only have an integral with respect to x, an integral with respect to y, because we've performed the integration to x with regards to x already. Then our MC we will now write as mxy. What this is, I will tell you in a second. And because we got rid of our exponential decay and of our common offset, we have only this thing still there. Now our mx, my is our complex initial condition, which was a function of r, so more explicitly of x, y, and z, integrated over this part of space that we are interested in. So let's say we have a z width, slice width of delta z, then that would be, if it's located exactly at some point z0, it would be like this. Yeah, so essentially what this means is, remember we had the equilibrium magnetization as a function. These are our initial conditions as a function of space, so as a function of x, y, and z. And now we're averaging these equilibrium magnetization, so the initial condition of our spinning magnetic moment, we average that over a slice in the z direction. Yeah. And so we project, like, so you can also view it like this. Maybe that's one way to view it. So we have our x and y plane, and we had our, so using the z gradient and our excitation, we excited a given slice, and now we average over z, so that's our z, so we take out this and then just get a representation of magnetization in the x and y plane, which for example, if its proton density might look, if you have the brain, look like that. So that's our mxy. Yeah, it's essentially our image function. Yeah, maybe let's stay a little bit with the mxy, because this will be the most important, or will be the fundamental thing that we're now interested in. So mxy is the equilibrium magnetization as function of space, of xy space. Yeah, so remember this was our initial condition which we tipped into the xy plane, so it's the initial condition in the xy plane for our spinning vector, magnetic moment vector, but it is dependent on space. And now you see the dependence not in terms of r, but in terms of in terms of x and y, meaning that the magnetization, so the proton density, remember the magnetization depends on how many protons there are. If there are more protons, the magnetization is higher because there's more thing to be magnetized by the static magnetic field, is a function of space. And if we, if some sample, for example the brain, has more proton density in certain parts of it in space, then if you make an image of that or plot it, then you see essentially what you're trying to image. Yeah, so that's our image function, in the sense that an image is a function over space. Yeah, it's not that we have. It's not the image that we create with MR. It's the, maybe this needs to be clear, it's the original image function. Yeah? So think of this now as the brain that has a higher proton density in certain parts of a slice in the Z direction and less protons in other parts. And we are trying to actually create an image of that. But this is the true but unknown, if you want, this is the true but unknown image, which we of course trying to image. Yeah? You know what I'm getting at? So there is something that we put into the scanner, and this has an intrinsic property, namely that the proton density varies over space. And how this proton density varies over space, this is what we're trying to, without slicing the whole thing open, cutting it open, and I don't know, using some chemicals to test how many protons there are. We're trying to, of course, using the whole MR setup to create an image of that. But of course, we also need to describe, or we need some entity that mathematically describes what we're actually trying to image. And this is for a given slice in the Z direction, this is this function. And this is the same thing that always came in terms of our initial conditions, yeah? Because the initial conditions are the equilibrium magnetization. Okay, I said it now 5 times. Please ask if it's not clear. It seems to be clear. Good, so that's the image function, and finally we do one final simplification, namely that we assume linear gradients. So last time we talked about different gradient functions that we can look at, and if we now assume that our delta B R T is given by a time-dependent contribution in the x domain, a linear contribution in the x domain, and a time-dependent in the y domain. Of course, we don't need the z here now, because this is integrated out already. Or you can also, if you are not happy with integrating the z out, just think this is for a very, very slim or thin slice in the z direction. So we only look at x and y gradients, and use the linear gradient forms that we established previously, and then we get the following. And then we get for our signal, we get the integral of x and y, our image function. So this describes the proton density of what we're actually trying to image, and we have our temporal integral, and now we plug in our gradient, our linear gradient function here for delta B. And this integrals with respect to dx, dy. And then we can do one final simplification, namely we can define the following terms, kx t as gamma divided by 2 pi 0t g x tau d tau. This is actually wrong here. This can't be a t, there must be a tau, because that's our integration variable here, t tau. So we integrate over. The x is obviously not a function of t, so we can take the x out and also the y out, and we can split this integral. So it makes sense to look at specific integrals with respect to only y and x. And if we use these definitions, then our MR signal equation takes the following form. Minus 2 pi, I minus 2 pi kxt plus k y t x missing. Dx dy. Yeah. And as we also have to stop here, which makes a lot of sense, is that what you see here is the 2D Fourier transform of our image function of mxy. So next time we will discuss 2D dimensional Fourier transforms. Of course, they are just the extension of 1D Fourier transforms into 2 dimensions. But from the development that we've seen so far is that if we assume that the MR signal acquires the bulk magnetization over space, this bulk magnetization being given by this integration with respect to spatial parts, and we have this means to change the magnetization at a given point in space, and over time, then we get to the fact that the signal that we acquire corresponds to the spatial frequency contribution at a given spatial frequency and orientation. So essentially, so maybe as an appetizer for the next session, so the signals that we acquire at a given time point are the weights in a linear combination of cosinoid basis functions. They are not like in the 1D case just cosines and sines. Remember that we build up complex signals by cosine and sines by adding, like in the Fourier series, adding many of them. In this case, the basis functions are not just the cosine and the sine, because these are 2D functions and we have to look at them a little bit closer. But essentially, the signal that we acquire are the weights of these basis functions. Meaning that if we know the weights of the basis functions and we know the basis functions, then we can reconstruct the image. But to this, we need to talk a little bit more about two-dimensional Fourier analysis. Other questions right now? No. Good. Then let's have a break and at 10:05 start with statistical methods.